Every single time you click a link, stream a show, or connect to Wi Fi, you are using this just incredible hidden system. Today, we're going to pull back the curtain and look at the most fundamental part of it all, the physical layer. It's the unseen engine that takes all those ones and zeros floating around in your computer and turns them into actual physical energy, light, electricity, radio waves that can literally race around the globe in the blink of an eye.
So here's our game plan. First, we'll get a handle on this unseen foundation. Then we'll break down its main jobs before we actually follow a single bit on its wild ride, from a digital idea to a physical signal. After that, we'll learn the language it speaks. And finally, we'll connect the dots and see why all this matters to you and the internet you use every day. Okay, let's dive right in. We're going down to the very bedrock of how the internet works, Layer 1. This is that critical point where the digital world meets the physical one. It's where all the abstract software and code finally has to become real. So what is it really? Well, the physical layer is the ground floor of what's called the OSI model, which is just a standard way of thinking about networking. I like to think of it as a super-focused mail carrier. Its one and only job is to grab a stream of ones and zeros from one device and get them over to another. It has no clue if it's carrying a piece of your email or a frame of a 4K movie. It just moves the bits. And this is where things get tangible. We're talking about hardware you can actually hold in your hand. The copper wires inside an Ethernet cable, the super thin glass of a fiber optic line, or the antennas in your router. The physical layer is all about turning those abstract bits into something real, a pulse of electricity, a flash of light, or a radio wave shooting through the air. So how on earth does it manage all this? Well, it all comes down to a really strict set of rules. You can think of this layer as the official rule book that every single piece of networking hardware on the planet has to follow to communicate. It really boils down to three main jobs. First, it defines all the physical characteristics. We're talking the exact shape of a plug, which pin does what, the precise voltage that means 1. Second, it handles the actual bit transmission, that little bit of magic where 1 becomes a pulse of light. And finally, it controls the data rate and synchronization. This is huge. It makes sure the sender and receiver are perfectly in sync, like two musicians tapping their feet to the exact same beat. All right, this is where it gets really cool. Let's get down to the nitty-gritty and actually trace the journey of a single bit as it moves through this layer. We're going to follow it from the second it leaves the digital world and becomes a real physical signal. So the process actually starts one layer up at the data link layer. It packages up data into something called a frame and hands it down. The physical layer gets this frame and immediately breaks it down into just a raw stream of ones and zeros. Then it encodes that stream into a signal, let's say an electrical pulse. That pulse zips down the cable. On the other end, the receiving device's physical layer does the exact same thing but in reverse. It detects the pulse, translates it back into a 1 or a 0, and passes it up the chain to get put back together. But how does that translation actually happen? I mean, how do you teach a 1 and a 0 to speak the language of electricity or light? Well, that is the art and science of encoding, and that's what we're jumping into next. Simply put, encoding is the dictionary that both the sender and the receiver have agreed to use. It's the specific set of rules for the translation. Without a shared encoding scheme, the signals one computer sends would just sound like total gibberish to another. Let's look at two classic examples. On the left, we have NRZ. It's super simple. High voltage is a 1, low voltage is a 0. But there's a huge problem. What if you have a long string of zeros? The line just goes flat, and the receiver can lose track of the timing, which messes everything up. Now look at the right. Manchester encoding is much smarter. It uses a transition in voltage for every bit. A drop from high to low could be a 1, a rise from low to high is a 0. The key is there's a change for every single bit, so the signal never goes silent. It has a built-in clock pulse that keeps both sides perfectly in sync. Of course, technology has come a long way since then. To get the blazing fast gigabit speeds we have today, we have to get way more creative. Modern Ethernet, for instance, can use incredibly advanced schemes like PAM5. Instead of just 2 voltage levels, on or off, it uses 5 distinct levels. This lets it cram multiple bits of information into a single signal change. It's how we push so much data through what's often just a simple copper wire. Okay, we have been deep in the technical weeds, so let's pull back up and connect all this to the stuff you use every single day. Why does any of this actually matter? It's actually pretty simple. That data rate and encoding scheme we were just talking about, yeah, that directly defines your internet speed. Those physical characteristics, that's the difference between you using a standard Ethernet cable versus a crazy fast fiber optic line. And all those rules for radio waves, that's what determines how good or how bad your Wi-Fi connection is. Pretty much everything you experience online is affected by choices made at this fundamental layer.
When you really boil it all down, the physical layer is the invisible workhorse of our entire connected world. It's the silent, unsung hero that makes everything else, from your emails to your video calls, even possible. Without these super detailed, agreed-upon rules for turning bits into physical reality, the internet as we know it just wouldn't exist.
So I'll just leave you with this thought. The next time you plug in that Ethernet cable or just connect to your Wi-Fi, take a second to think about the incredible journey your data is about to take, as tiny pulses of light or invisible waves of electricity, all just to bring the world to your screen. Thanks so much for tuning in.